Welcome to the MH2801 video segment on different conventions for the Fourier transform. Okay, in the literature, in different textbooks, we sometimes find different conventions for the Fourier transform, and you need to understand that different people use different conventions for the Fourier transform because it suits their needs. So in this course, in the old lecture notes, we have been following the conventions set in Afkan and Weber, which is a textbook for mathematical methods for physics students. And then, but since we have moved on to read Riley, Hobson, and Benz, we also need to understand that there is also another possible convention that we can use for the Fourier transform. There is no one convention that's better than the other. It depends on your need, but you just have to understand that if you start with one convention, you should stick to it, especially when you are ready to do both Fourier transform as well as inverse Fourier transform. Now in Afkan and Weber, the Fourier transform is defined in this following manner. So f of twiddle of omega, which is the Fourier transform of f of t, is written as the integral from minus infinity to infinity f of t e plus I omega t dt. Okay, so the key thing to note is first the plus sign in the complex exponential. Now the other thing to note in for the convention for from Afkan and Weber is the normalization, which is 1 over square root 2 pi that appears in front of the integral that defines the Fourier transform. Now in Riley, Hobson, and Benz, this Fourier transform is written as 1 over square root 2 pi into integral from minus infinity to infinity f of t e minus I omega t dt. Okay, so note that the Riley, Hobson, and Benz convention differs from the Afkan and Weber convention by the minus sign in the complex exponential, but otherwise the normalization is exactly the same. Now the Riley and Hobson Benz convention has the advantage that it is similar to the definition of the complex Fourier coefficients, which is Cn equals to 1 over t and integral from 0 to t of ft e minus I 2 pi n t over capital T dt. So notice the minus sign over here. So this is also a minus sign in the complex exponential. Now whichever convention you use, it is okay, so long as you remember to flip the sign of the complex exponential when you go to the inverse Fourier transform, which gives the function f of t in terms of its Fourier transform f twiddle of omega. In Afkan and Weber, this would be 1 over square root 2 pi, the integral from minus infinity to infinity, f twiddle of omega, e minus I omega t d omega. Now obviously we have to change the integral from an integral over time to an integral over frequency, but we also need to change the plus sign in the complex exponential to a minus sign in order to perform the inverse Fourier transform. But otherwise the normalization constant remains the same as 1 over square root 2 pi. Now if we use the convention of Riley, Hobson, and Benz, then the inverse Fourier transform will be 1 over square root 2 pi, ft being 1 over square root 2 pi, the integral from minus infinity to infinity, f twiddle of omega e plus I omega t d omega. So the most important thing to note is the switching of the sign from plus to minus. So same here and same in the Riley, Hobson, and Benz. So it doesn't matter whether you start out with plus or a minus sign in your Fourier transform, so long as you remember to flip the sign when you go to the inverse Fourier transform, you are okay. Now, what other conventions do we have for the Fourier transform? Now, another convention has to do with the normalization constant. So, another convention not found in these two textbooks, of course, but you will find them in other textbooks. For example, textbooks on quantum mechanics, textbooks on solid-state physics, as well as textbooks on optics. Okay, you'll find this particular convention, which is F twiddle of omega equals to an integral from minus infinity to infinity f of t e I omega t dt. So note that this definition of the Fourier transform has a unit normalization factor out in front of the integral. Otherwise, it will be the same as in the Afghan and Weber or Riley, Hobson, and Benz. And in the definitions, in the conventions used by Afghan and Weber, as well as Riley, Hobson, and Benz, the normalization constant is symmetric with respect to Fourier transform and inverse Fourier transform. In this case, it is asymmetric. The Fourier transform has a normalization constant of 1, but the inverse Fourier transform, f of t, is equals to 1 over 2 pi, an integral from minus infinity to infinity, f of f twiddle of omega e minus I omega t d omega. So you just need to note that there's a change of integration variable from t to omega. There's a change of sign from plus to minus, and then there is a change of the normalization constant from 1 to 1 over 2 pi. This is the other convention that is frequently used in different kinds of textbooks. Now there's one more convention that I need to talk about, and that is the convention between the signs for x and for k. So, so far we have written, say, the Fourier transform of a function f of t, and we write it down as f twiddle of omega, and this is 1 over square root 2 pi, the integral from minus infinity to infinity, f of t e I omega t dt. Okay, so so let us note it down that usually t plays the role of time, and then omega plays the role of frequency. So these two are reciprocal variables. Time has a unit of seconds, and then the frequency has a unit of second inverse. Okay, so this is the definition of the Fourier transform with respect to a function of time. But of course, we can pretend that this definition of the Fourier transform applies to any kind of function. So, for example, if we want to write the Fourier transform f twiddle of k of a function of space, so we will again write this as 1 over square root 2 pi, the integral from minus infinity to infinity, f x e I kx dx. So we don't change any sign, but just replace. We just replace t by x. So this is now space. Okay, and k is actually the wave number. Okay, so what we do is we will just replace 1 for 1. So x goes to t and omega goes to k. But okay, now there is a reason why some people actually prefer to have separate different signs for different Fourier transforms, and that has to do with the fact that in a traveling wave, we frequently write the relationship between x and omega in this particular form. So this is a right moving wave, and it is given by an exponential I k times x minus omega times t. So you notice that omega and t and x, the complex exponential comes with plus sign here and a minus sign here, which is why some textbooks, if they are writing down the Fourier transform for a function of time, they would write this as an integral from minus infinity to infinity, ft e minus I omega t dt. But in the same textbook, if they are doing the Fourier transform of a function of space, then they will write its Fourier transform f twiddle of k as the integral from minus infinity to infinity, fx e I kx dx. So notice that they have different signs. They have different signs for whether, depending on whether it is a function of time or a function of space. So this you might see more frequently in QM or optics textbooks, because in those kind of cases, because we're dealing with waves, both x and t appears together. For other kind of problems where you deal either with time alone or x alone, then previous conventions are frequently used.